move on to the third talk in the session, which will be given by Wenhao on growth and capabilities as modal effects.
Thanks for the introduction. So I'm going to talk about how to encode different effect systems into modal effects. This is joint work with Lindley. So what are effects? They are the way that the programs interact with the environment. And many examples. Effect types, also called effect systems, statically track the use of effects in types. And there are many different kinds of effect systems. Perhaps two of the most popular ones are either based on role types, as in the language COCA, or capabilities, as in the language effect. So in COCA, every function type from A to B is annotated with an effect role E, which represents the effects that might be used when the function is applied. And in effect, functions are called blocks, which are second class, using this double arrow. And it not only binds a list of normal arguments of type A, but also a list of capabilities F of type T. So a blocking effect can call this capabilities F bound here, and may also call some other capabilities provided by the context. So as we can see here, their function types look quite different, and it is not obvious how to encode between them. And I think the main challenge is that their effect tracking mechanisms are deeply entangled with function types. This is reminiscent of the classical situation of encoding between call by value and call by name, because when two sunk and or false computations is entangled with functions in call by value and call by name. The great work on call by push value subsumes both by decoupling sunken and falsing from functions. So why don't we do this for effect tracking? Why don't we decouple effect tracking from functions? This is what our previous work did. So we have this Uppsala paper on modal effect types, which decouple effect tracking from function types using modalities. And this paper shows that how such a system can significantly reduce the verbosity of effect polymorphism in traditional systems. And in this work, we do something different. We propose a uniform framework to encode and compare different effect systems based on the idea of modal effect types. So these are what our encodings look like. So for function types in COCA and effect, we encode them as function types in math with some actual modalities written as these square brackets or angle brackets to explicitly simulate how effect tracking works in different systems. And in the remaining of this talk, I'll try to explain what it does. So what are modal effect types? The key idea is to have a notion of ambient effect context, which are the effects provided by the context. So here is the typing judgment of a first-order function. It takes an integer x, calls the yield operation, returns a unit. This add syntax tells us that the current effect context is yield, so we can call the yield operation. Here is another example of a higher order function. It takes a function argument f of type int to unit, an integer x, applies f to x, add the ambient effect context yield. So effect context is propagated through types and terms. So for this higher order function, both the argument function and the result function are at the ambient effect context yield. And there is a natural notion of sub-effecting. So say that we have a function that only calls yield, we can of course type check it at a larger context with both yield and ask operation. Keep in mind that effect contexts are part of typing judgments. They are not part of types. And whenever we want to track effects in types, we use modalities. We have absolute modality written as a square bracket with some effects E. It changes the ambient effect context to E. So here is a function whose ambient effect context is only ask, And we use the mode syntax to introduce the absolute modality of yield, which changes the ambient effect context from ask to yield. So for the premise, its effect context is yield. It also introduces a knock in the context, which I'll explain later. And we also have relative modalities written as angle brackets E. It extends the ambient effect context with some new effects. So here we have a function which uses both the yield and ask operations, but the ambient effect context has only ask. We use this mode syntax to introduce the relative modality of yield. So for the premise, for the inner function, its effect context contains both ask and yield. And it also introduces a knock into the context. These knocks control the accessibility of variables. So here is an example of an invalid judgment. It is unsafe because we have a function argument in the context whose effect context is ask. It may use the ask operation, but we want to call it instead the absolute modality of yield, where only the yield operation is present. Mat rejects its expected premise by not allowing the function argument f to be used after the knock of the absolute modality of yield. So these knocks control which variables can be used and which variables cannot. In order to make it well-typed, we can annotate the variable bounding of f with the empty absolute modality, which tells us that f is actually not at the ambient effect context of yield, but at the empty context. So it is a pure function. We can use it wherever we want. And such a bounding is introduced by modality elimination. Supposing we have a value v, which is a function from into unit with the empty absolute modality, we can use the net mode syntax to eliminate the modality. So we have a bounding f, a function from into unit with the annotation of the empty absolute modality. So these are the main ideas of modal effect types. If you get lost, don't worry, because now we are moving to encodings. So first we'll encode rows as modal effects. So we consider the Kalkner system F epsilon, which formalizes the Kokas row-based effect system. The idea, as I have mentioned, is to allocate each function arrow with a row of effects E, which represent which effects might be used in this function. I'll give some examples of system F epsilon. So this is a first order function, takes integral x, calls the yield operation with the argument x. So it has a function type from into unit annotated with yield, which is the operation that is used inside this function. And here is a higher order polymorphic function. It's the standard application function, but abstracts over an effect variable epsilon. So the argument function f might use effects epsilon, and the result function may also use the effects epsilon because the result function calls the argument f in the function body. For the middle arrow, it's a pure. Its effect annotation is empty because the middle function does not call f directly. So our encodings for system epsilon is very simple. It encodes an effect for function type in system F epsilon as a function type in mat with an extra absolute modality with the same effect. So for the first order function, we encoded it as a function type from into unit with the absolute modality of yield to reflect that it is a function that may use and may only use the yield operation. For the encoding of the term, we just use the mode syntax to introduce this modality. For the second example of the higher order function, it is similar. So the higher order function has 3 function arrows. We introduce 3 absolute modalities, one for each function arrow. For the argument function and for the result function, they both use the absolute modality of epsilon because both these functions can use effects in epsilon. And for the middle arrow, we use this empty absolute modality because it is the pure function. And the encodings preserve polymorphism. So for the quantifier of the effect variable epsilon, we just preserve it in the encoding weight. Yes, and for the term, it is still very similar. Module knows this mode and net mode syntax, which explicitly introduce and alienated modalities. So as we can see here, our encodings kind of use modalities to explicitly simulate what effect tracking does in system F epsilon. Okay, now we encode capabilities as the modal effects. We consider the calculus system C. It is the core calculus of effect. As I have mentioned, the idea is to treat effects as capabilities provided by the context. So a block, which is a second-class function, binds a list of arguments of type A and a list of capabilities F of type T, and returns some value of type B. So I'll give some examples. The first one is, again, a first-order block. It calls the capability yield provided by the context. So in system C, we use these curly braces to create a block. It takes an integer x and applies the capability yield to x. Its type is just int to unit, because system C allows blocks to use arbitrary capabilities from the context without mentioning them in the type. And here is a higher order block. It not only binds a value variable x, but also a capability variable f from int to unit and applies f to x. So the binding of the capability f not only appears in terms, but also in types. So it is kind of similar to some form of dependent types where we have bindings where we have term level bindings in types, and may mention it later. So blocks are second class, they cannot escape. So if we look at the example of this application block, we can call the capability f in the block body, but we cannot return it because returning f would allow f to escape its lexical scope. So in order to write a current version of this block, we need to use boxes. So for this new higher order block, it binds the capability f and it returns another block from x to f of x. And we box it in order to make a second class block into a first class value. So the type of this return value is int to unit at f. It's a block from int to unit, and the at f syntax tells us that this block uses the capability f. So as we can see from this signature, types in system C can bind some variables and can mention these variables later. Our encodings of system C look like this. It is very involved because a block construction system C does several different things. So for this example first, it binds a capability variable f. This variable f both appear in terms and in types. The block body may call this capability f, and the block body is also allowed to call some arbitrary capabilities from the context. Our encodings make these different things explicit. So for the first one, we introduce a type level variable f star and wrap the argument with the absolute modality of f star. So by having a type variable here, we are able to mention the term variable f at the type level So it is similar to singleton types, if you know what singleton types are. And by wrapping the argument with the absolute modality of f star, we make sure that whenever we call this argument, f star must be present in the context. And for 2 and 3, we use the relative modality of f star to wrap the whole function. So first, we use a relative modality which extends the ambient effect context with f star, so we allow this block body to call f star. And second, because it is a relative modality, other effects provided by the context can still be used. And for encodings for boxes in system C, we encode them as absolute modalities. So for the current version of the application block, the return type int3unit at f is encoded as a function type from int3unit with the absolute modality of f star. So which tells us that this return function may use the capability f. So let's wrap up. Now we have seen some examples of encodings of system F epsilon and system C into MET. By observing these encodings, by only observing the encodings of these types, we can have some interesting observations. So first, different top-level modalities are used in the encoding of different types. For system F epsilon, every function type is encoded as a function type with an absolute modality. Well, for system C, function types are encoded as a function type with a relative modality. And we only use an absolute modality in system C if we have a box type. So it tells us that in system F epsilon, function types always fully specify which effects might be used. While in system C, block types never fully specify which capabilities might be used. You can use arbitrary capabilities from the context without mentioning them in types. And we only fully specify the capabilities they use when we box them. The second observation is that effect variables are inserted at different positions. In system F epsilon, the encodings use effect variables only if the source type uses effect variables. But for system C, whenever we encode a function type, we introduce a list of effect variables. So it tells us that capability variables in system C performs some role, are kind of like some explicit form of effect polymorphism. And it explains why, like, if you look at some code neighbors of effect, you'll never find explicit effect variables because capabilities can do complete rules of effect variables. Yeah, we have more things in the paper. We have the full formalization of the uniform framework, which we call MAT-X. And X is an effect structure. So it is a parameterized variable following some previous work, which allows us to abstract over different treatment of effect collections, which are orthogonal to how they track effects. And we have some extensions to make our framework more expressive to include more other systems, and some standard meta theory of type summoners effect safety. And we have encodings of various different systems, including 2 core calculi of Coca and 2 core calculi of effect. So I have only shown encodings of function types in the talk, but we also encoded effect handlers. And we proved these encodings preserve types and semantics. And I think that's all of my talk. My takeaway is we should decouple effect tracking from function types, and by doing so, we can have a uniform expressive framework which subsumes existing effect systems. Thank you.
All All right, thank you. Any questions? Yeah.
A beginner question. In the Coca translation, I would expect the E absolute modality to be on B, and not on the whole function type. Why is it on the whole function type?
Why it is on? You expect it to be assigned B.
I would have guessed A arrow E B.
Right. So a modality overrides. So a modality overrides the whole effect context. So by having an absolute modality here, we are seeing that for the function from A to B, its effect context becomes E. And this effect context E propagates through type structures. So it is a function that might invoke effect E. But if we mode this absolute modality inside this function, then it means something different.
I have another question if you don't have. So I expect that it's possible to make a monadic translation for the Coca effect system. So you start with the effect system and you go into monads in a system with no explicit effect system, but monads to represent the effects. And I was wondering whether we could factor the monadic translation through your translation. So maybe the usual monadic translation, if it exists, could be defined after your translation.
Sorry, I didn't quite answer the question.
Okay.
Answer that?
No. I think there's a bit of a misunderstanding there. There's not really a fundamental difference between the presentation of effect type systems where you write the E on the arrow versus the Wadler style where you write T of E applied to B. There's something quite different going on here. The modal effects are contextualizing all of the effects. So you don't gain anything by trying to do the thing that you're suggesting. That's not actually doing the decoupling that we're going for. But we can talk more about that offline if you like.
I have a quick question. So I might be misremembering, but I have notes from your Uppsala talk. And I have written down here that you originally designed the MET system to try and subsume effect polymorphism, so you explicitly didn't want this as a feature of the type system, and then you of course added it here to correctly model this thing. So was it originally there? Like, did you expect that you needed it?
Yes, so if we want to fully simulate traditional effect systems, we do need effect polymorphism in MET. But our Uppsala paper shows that, so in our Uppsala paper, we identified a large fragment of traditional effect system and encoded it into MET without effect variables. So it is not the full system, but a subset of traditional effect system. Yes.
I mean, a quick question. I mean, it was very impressive and also enigmatic. So I was wondering whether you have in mind at some point to look for some kind of semantics, like monads, and what you do is so much beyond. I mean, and looks like extraordinary. It would be interesting to have a mathematical description of what you mean. Yes. I mean, typically this polymorphism and effects, and you graph the whole map, the whole arrow, and how you could try to describe that using tools of, let's say, semantics, categorical semantics. So. I mean, okay. I mean, in a way, the success of monads is that they are beautiful for programming and also they are beautiful mathematical models. Mm-hmm. So I'm just wondering whether you have that in mind. That's it.
I don't, but I do want to. I don't for now, but like the whole calculus is based on some quite theoretical work on multimodal type theory, which does have a categorical semantics, and I expect we could generalize their categorical semantics for this work. So yeah, I think there's some future work to be done. Okay.
All right, so I think we should move on. So thanks, Wenhao, again.